Now, our next step will be to to give you an example that actually has cross couplings. Because again, once you go into that domain, you're losing the G parameters. Now we only have the transfer function to work with. So here's an illustrative example. I'm going to work with you guys for a second order filter that it will include two transmission zeros. The topology of the filter is shown right here. So I basically have two resonators shown as 1 and 2. I have, of course, my direct couplings as I have before. So I have 1, 2, 3 direct couplings. And I have introduced with this red color an additional cross coupling, directly basically creating a path from the source to the load. My assumption is going to be exactly the same as before, lossless resonators and synchronously tuned resonators. All right, so when you basically try to synthesize a second order filter, as we have seen from simpler examples, I'm still dealing with a 4x4 coupling matrix. And the big difference between what we saw before and this one is this M03 that is basically non-zero. That represents a direct coupling between the source to the load. The transfer function is going to include basically two poles. It's a second order, and two transmission zeros, which you will see in the numerator. So both the numerator and the denominator are basically second order polynomials. Now, you can choose where your transmission zeros lie and where your poles lie, right? That depends exactly on what type of transfer function you want to implement. I have basically made a particular example here where I have basically chosen my two poles down here on the left-hand plane, and then two transmission zeros symmetrically located right here. So if those are the two zeros and two poles that I have, the transfer function I'm basically trying to implement is shown at this point. And the rest is basically very similar to what we did before. Again, you can employ any symbolic calculator you like. This is going to be the S21, and you equate that with the transfer function, and it will give you an explicit solution for the coupling parameters M. Now, indeed, if you go ahead and you plot that in the normalized domain, remember we're still doing things at the omega is equal to 1 domain. We haven't seen scalings yet. You will very clearly see the two reflection zeros here that are due to the poles, and the two transmission zeros right here. This is also a slide that basically shows you very explicitly where the poles and zeros are for those of you who would basically like to see this.